Hey, so welcome everyone. Today we will continue on with the kinematic analysis of planar mechanisms, and basically we will talk about the graphical method, so that's why it is only applicable for planar mechanism systems. And basically we continue on from last week. So we introduced the idea of relative instantaneous center of velocity, and we will apply it for the analysis of planar mechanisms. And what we also introduced is the so-called Aronhold-Kennedy theorem, which says that if we have three rigid bodies and they are moving in the plane, so they are performing planar motion, then there will be three instantaneous relative center of velocities, and they will be collinear, so they will be situated on one single straight line. So that is what we have so far. And now we will take a look again on the example of a four-bar mechanism, and we will introduce a new algorithmic way to count the number of Aronhold-Kennedy lines and to manage the relative poles or relative instantaneous velocities. So we will have an algorithmic method, and in parallel we will take the same example as we had last week. So we have a four-bar mechanism, and the numbering is 1, 2 and 3. We have three moving rigid bodies, and we have one ground which is fixed, so it is not moving, let's say. And in the algorithmic method we introduce some graphical technique. So first we draw a circle, and the circle itself is representing the mechanism, the whole mechanism itself. So this is the mechanism. And the next thing what we do is to draw some points on the circle, and these points will represent each rigid body or each link. Okay, so circle points, the points represent the links, the rigid bodies. And accordingly we will have numbering which is identical with the numbering of the link. So this will be responsible for link number 0, which is the ground. This point is playing the role of link number 1. This is playing the role of link number 2, and finally link number 3. So this is what we have so far. And then we can draw the so-called relative poles or relative instantaneous center of velocities, and these will be lines on this graph. So the lines are playing the role of the relative instantaneous center of velocity. For example, I can draw the point P01 here, and accordingly we have this line here. So P01 point can be represented by a line in this graph, and so on. So we can also draw P1, 2. These will be all the so-called trivial relative poles. Okay, so P1, 2 is here. P1, 2. Actually, this notation is not necessary here because it's connecting 1 and 2, so therefore it's trivial that this is P1, 2 and P. But for first time we can show it. So this line is P2, 3, and finally we have P0, 4 here. So this is what we have so far, and these are, we said, trivial poles because it's easy to put and we don't need the Aronhold-Kennedy theorem. So P10, P12, P23 and P04 were trivial to find. And then what we also have are triangles in this figure. So we also have some triangles, and this helps us to manage the Aronhold-Kennedy lines. So each triangle in the figure corresponds to an Aronhold-Kennedy line, or just simply Kennedy lines. And I will use color for this. For example, if I draw this triangle here, let's see, powerful color. So let's say we have a triangle here, and this triangle will be 0, 1, 2 triangle. So this is the this is responsible for Kennedy line 0, 1, 2, and as we can see, and this is the application of this whole figure. So as we said, in a Kennedy line there will be 3 points, but if I have 2 points, they already define the Kennedy line itself. So if I have a triangle of which 2 sides are defined, it means that I am able to create the Kennedy line on the graph of the mechanism. So here P10 is already known, P12 is already known, so I am able 0, 1 and 1, 2. I am able to draw the corresponding Kennedy line, which is here. This is Kennedy line 0, 1 and 2, and I can do the same. I hope I will not run out of colors. So I can do the same with this Kennedy line, which is 0, 2 and 3 Kennedy line, and accordingly I can draw in the figure. So 0, 4 and 2, 3 are the points in which the Kennedy line goes through. So this is Kennedy line 0, sorry, not 0, 0, 2, 3. Yeah, 0, 2, 3. We can see here the indexes. Okay, 0, 2 and 3, and it goes through P2, 3 and P0, 4. And the message is that the important thing is that if I would like to find this instantaneous center of velocity, or relative instantaneous, so I'm going to find this, and this is P02, then this graph shows me that this line, this point is in the intersection of the red and the blue Kennedy line. So if I try to find this intersection point, then it turns out this point P02 is situated here. Okay, so this is how to apply this graph. And to make it a bit more clear, we try to create the same for the missing point, which is this is the last one. Okay, so we have to find 2 points with the Aronhold-Kennedy theorem. It is already done, and we also would like to find P13, and in this graph P13 is this dashed line, so this is P13, and it tells us that first I should try to find the Kennedy line 0, 1 and 3. Okay, so now I'm going to draw this triangle with green. Okay, so this green one is the Kennedy line 0, 1 and 3, and it goes through P01 and P04, so I can draw it here, and this is Kennedy line 0, 0, 1 and 3, Kennedy line 0, 1 and 3. It is already done, and finally I will draw it with dashed line. So this will be the last Kennedy line what we can draw. So this triangle represents the Kennedy line, of which the indexes are 1, 2 and 3. 1, 2 and 3, and it goes through point P12 and P23, which are already done in the figure. So P12 and P23 are here and here, so the last Kennedy line goes like this, and this is Kennedy line 1, 2 and 3. It's already in the figure, and as we can see, the intersection point of Kennedy lines 0, 1, 3 and 1, 2, 3 gives us the location of point P13. So this is where we can draw P13. So this is how to apply this this graph. It's totally abstract, and this is the meaning of the points, lines and triangles, and there is a relation between the abstract drawing and between the real physical system. Okay, and it only helps us to manage and keep in mind which points are intersects with which Kennedy lines and so on, but it can be really helpful when the system is complicated. And let's try to apply it for a okay, there's a comment about some administrative stuff. At the end I will talk about it. Okay, and now we will move on with an example which is not as trivial as this one. So we have an example where this Aronhold-Kennedy theorem really helps to calculate the things. So we have a mechanism for which there is a straight bar here, and basically we say that this is the input motion. It rotates with angular velocity 1, and then another straight bar is attached with a revolute joint, and then there is a slider, and this was the first and this is the second link in the mechanism, and the slider is a third rigid body, but it is also fixed rigidly to another bar, so they are welded here, let's say, and therefore this angle is always 90 degrees. Okay, that's very important. So this slider moves together with this rod, they are rigidly fixed together, and the output is this angular velocity omega 3. Okay, so the input is omega 1, the output is omega 3, and the question is to find the relation between them. Okay, so the question is how to find the output angle or output angular velocity as a function of the input velocity, and also we have to include the input angle. So naturally there is the angle here which is the input angle, and the question is how to find the output angular velocity if these two things are given. And first we just create a very quick analysis of the system just to find the degrees of freedom and everything. So this is the graph of the whole structure. We also have to introduce the numbering of the ground. So we have 4 rigid bodies, the ground, and 3 moving links, and basically we have 4 joints, and joint A connects the ground and the first moving body, joint B connects the first and the second, and joint C connects the third and the second, and joint D connects the ground with rigid body number 3. Okay, so this is the graph of the system, and we can also introduce we can also calculate the number of degrees of freedom by calculating the number of joints. So let's count the number of full joints. So this is a full joint, this is a full joint, and this is also a full joint. And here we also have a full joint because it allows only 1 degree of freedom. It can only slide in this direction and no other type of motion. So it cannot rotate and it cannot move perpendicularly. So basically all of them are full joints. Sorry, the order is A, B, C, D. And the number of links is 4 basically. So by using the Kurzbach equation we can say that the mobility is equal to the, so we have done it at the beginning of the semester. I know that it was long ago, but these are easy things. So the mobility or the degrees of freedom is equal to 3 times the number of moving links. So this is 4 minus 1, because 1 link is the ground, minus 2 times, the formula was just used in the beginning of the semester, we have the general formula, and now we substitute everything. So 2 times 4. Okay, so this is the number of joints, and this is 9 minus 8, which is 1. So we have 1 degree of freedom, and we can also separate the structure into groups just to check if everything is fine. I know it was also long ago, but we can just remind ourselves. So as we said, this is the driven link, which is link number 1. Sorry, no, this is the driving link. Link number 1 is the driving link. It drives the whole mechanisms, and the driven link, the other links which are moved by the driving link, are 2 and 3. And so we have 1 driving link, which is fine, and we have 2 driven link. And as we said, I think you may remember, the number of full joints is equal to 3 over 2 times the number of driven links. Okay, so it is just coming here, which is 3. So if we are create this separation into groups, then there should be 2 links in the driven part with 3 joints, and it really works. So this will be the driven part of the mechanism, and yeah, this is really containing 3 joints, 1, 2 and 3, and 2 links. So everything is fine, the grouping works, so it means that most likely the degrees of freedom calculation was correct, so there is no any paradox in the mechanism. So we can say that we have 1 degree of freedom, which is important to know, and therefore it is really working thing. So there is 1 single input and 1 single output, and we know that the number of inputs should be equal to the number of degrees of freedom, but it really works now. And what we do is to just check first how to solve this problem analytically with some analytical equations. Okay, so we can solve the problem analytically. So we can just create some equations and we can solve it. For example, and this we should be familiar from the course called dynamics. So we can calculate the velocity of point B. So VB is equal to VA, which is 0, plus omega 1 cross the position vector from A to B. Okay, we have this equation, and we can calculate the velocity of point B very quickly and nicely. So it will be something like this. It will be perpendicular to the bar, of course, so it can be calculated. And then we have a closed loop, so we know the velocity here and here, but we don't know anything about the angular velocity, so we can introduce the angular velocity here, which is omega 2, but we don't know them. But we can try to calculate the velocity of point C, and first we should start from here, and then we start from here, and we will obtain 2 equations. So first we say that the velocity of point C is equal to, I will have some extension here, the velocity of point C is equal to VB plus, using the same formula, omega 2 cross the position vector from B to C. And this will be the velocity of point C, but the question arises, which C point is this? because there are two rigid bodies here and they are overlapping each other. So we can talk about the velocity of point C, which is situated on link number 2, and we can also speak about the velocity of point C, which is located in rigid body number 3, and they have different speed because rigid body 3 and 2 have a relative velocity to each other. So finally we have to extend this equation, because we say that this whole part here is the velocity of point C located in rigid body number 2, but we would like to calculate the velocity of point C located on rigid body 3, because we will have some other equation when we are coming from the opposite direction. So this velocity could be easily calculated by this formula. So this is Vd plus omega 3 cross RdC. So this equation is ready, and this is very nice. We don't have to do anything here. So we could calculate the velocity point C if we would have information about this angular velocity, but we don't have. So this is an unknown in this equation, so we are not able to calculate the velocity of point C3. Therefore we need another equation, and we come from this direction here. But here we already calculated the velocity of point C of rigid body number 2, and then we need an additional term, which is the so-called relative velocity, and we mean that this is the velocity of point C3 relative to rigid body number 2. Okay, so this is a relative velocity, and this is relative to rigid body number 2. And this whole velocity term represents the velocity of rigid body number 2 in point C. So we have these equations, and the unknowns are the angular velocities, and unfortunately we have some unknowns here. So these are, and this is also unknown actually. So the unknowns are VC3x, VC3y, and also the magnitude of the angular velocities are unknown. The direction is well known because they are perpendicular to the whiteboard, but we don't know the magnitude of them. And the direction of this relative speed is also a known thing. So beta C3 has this direction, but the magnitude again is unknown. So BC3 scalar variable is unknown. So we have 5 unknowns and 2 times 2 equations, which is basically 4 scalar equations. So we have one more equation, and the additional information is that this rod is always perpendicular to this one. Therefore, we can say that the two angular velocities are always the same. So if I'm just turning the third rod, the second rod will turn or rotate with the same angular velocity. So the last equation is this one, and this is one more scalar equation. So finally we have 5 equations and 5 unknowns, so it is possible to calculate everything. But it is quite hard to manage so much equations. So therefore people introduce some geometric approaches to similar problems, and this is what we will address now. So now we will solve the same problem and we will apply the Aronhold-Kennedy theorem to do the same calculation graphically. Okay, so this was just a reminder from dynamics course. There is nothing new here. But the new part will be to solve the same problem by a graphical method, the same problem solved by or solved graphically. So we should try to apply this algorithmic way. So I'm drawing a circle which represents the whole mechanism, and again we will have 4 points because there is 4 links in the mechanism, and the numbering will be 0, 1, 2 and 3. So this is the mechanism itself. And then the next step is to imagine how we can calculate the output velocity omega 3 as a function of the input velocity omega 1. So we need some idea and we will think about the whole problem a little bit more general. So there are 2 rigid bodies. This is omega 1 angular velocity for rigid body number 1, and this is rigid body number 3, and we assume that it also has some rigid body, also have some angular velocity. And from the Aronhold-Kennedy theorem, we know that there should be a line on which 3 relative instantaneous center of velocities are situated. And what we have to know is that there is also a rigid body called ground, or rigid body 0, and then we know that basically this velocity, which is an absolute velocity, is a relative velocity relative to the ground. So this means that this is an angular velocity of rigid body number 3 relative to the ground, of which the index is 0. And this is the same here, so we can say that this is a relative velocity relative to the ground. And then we will know that there is some point where it is fixed to the ground, like here. Okay, so this is P01. So this is the point. Basically this is identical with point A. This is the point where this whole body is fixed to the ground, and the third body is also fixed to the ground, so this will be P03, and this point is identical with point D. This is the point where it is fixed to the ground, and we can assume, based on the Aronhold-Kennedy theorem, that there will be somewhere an instantaneous relative center of velocity called P13, and its meaning is that, so knowing the definition of instantaneous relative center of velocity, we know that the velocity of the 2 rigid bodies 1 and 3 are equal to each other here at this point. So finally I can say that here the velocity must be equal, and I also know that these 3 points are located in the same line, and basically the name of the line is Kennedy line 013. Okay, and we know that the velocity is equal to each other here. From our earlier mechanical studies we also know that if it is fixed here, then this should be perpendicular here, and we also know that the velocity is 0 here, so finally we can draw this line which tells us the velocity of each point of rigid body number 3, and we can say the same for rigid body number 1. So each point can, the velocity in each point can be calculated, and basically this this slope is related to omega 1, and this other slope here is related to omega 3, and finally we can create a formula. So let's say this is the velocity of P13 here in the middle. Actually I could use some other color if I want. So this is the velocity P13, and basically we can compute it in two ways. So the velocity of P13 is equal to the distance here times the angular velocity omega 1. So this is omega 1 times the distance from P, or let's say A, okay, that would be easier. So the distance from A to P13, this is the distance, and this is equal actually to omega 3 times the distance from D to P13. And therefore we know that the ratio, sorry, this is omega 3, the ratio of omega 1 and omega 3 is the distance from D to P over the distance from A to P. Okay, so this is the goal, what we want to do. We would like to apply this formula, and for this we only have to know where is this point, which is the relative instantaneous center of velocity of rigid body number 1 and number 3. So we would like to accomplish this this formula, and the basic question is to find P13. Okay, so that's the, where is P13? So if we can answer this question, then we can answer the whole problem. We can answer the question of the whole problem, which was basically to calculate the omega 3 as a function of the omega 1 velocity. Okay, so this is what we want, and I can make a drawing here. So P13 is represented by this line in this graph. I don't want to use the notations because it would be too crowded. Maybe we can try. Okay, so this is P13. So we are looking for this relative pole. I hope it was understandable so far. And now we go back here and try to find this point with the help of the Aronhold-Kennedy theorem. So first we should collect again the trivial relative poles. Okay, so the trivial poles are, for example, here, this is, as we said, this is identical with point A, and basically this is also the absolute instantaneous center of velocity for rigid body number 1, because this is fixed here to the ground and the ground is fixed. Okay, so P01 is trivial, and we can draw it here. P01 is a trivial pole, we can draw it here, and then here rigid body number 1 and 2 are connected, so this is P12. It is also trivial because there is a joint, a rotational joint, so it is very easy to say that this is P12. Okay, it was P01, this is P12, 1, 2, and the last one is here, what we can say easily. So this point, which is identical with point D, is P03, but it is actually identical with the absolute instantaneous center of velocity of rigid body number 3, because it is fixed to the ground here. So P03 is also a trivial relative pole, and its location is well known. And now we see that if we want to find this relative pole with which we can accomplish this whole calculation, if we want to find this relative pole, then basically we could find this Kennedy line, which represented this triangle, because this is already known. So this Kennedy line, which is 0, 1, 3, this is Kennedy line 0, 1, 3, is already known because it goes through P01 and P03. So the blue Kennedy line is basically well known now. I mean, we can construct it easily. Okay, so this blue one is Kennedy line 0, 1, 3. Okay, so we know that this is the intersection, we know that the Kennedy line 0, 1, 3 goes through P01 and P03, and if these 2 points are given, then we can construct the Kennedy line. This is ready. And then we also know that we will find this P13 point if we could somehow define this missing Kennedy line. So the next step, it would be to find this green Kennedy line. Okay, we can just put the steps here. So first we found the trivial poles, and then we found Kennedy line 0, 1, 3, and the next step would be to find the Kennedy line 1, 2, and 3. We should find Kennedy line 1, 2, 3, because the P13 is the intersection point of Kennedy line 0, 1, 3 here, and Kennedy line 1, 2, and 3. Okay, so therefore we would like to find this Kennedy line, and from the figure I can easily see that if I would like to find this Kennedy line, I have to find at least one more side of the triangle, and this is, we don't have any hope to find this now, but we may have some hope to find this point here. So the next step is to find P23. Okay, so if we find P23, then it's okay. So if we would be able to find this P23 point, then we would be able to define the Kennedy line 1, 2, and 3. Actually, I could change this, or I can create a box. Just to make it easier to understand everything. Okay, and this dashed line is representing the missing point P23, and P23 basically is the relative instantaneous center of velocity of rigid body number 2 and 3. And how to find it. So that will be the next step. We will create another separate drawing just to help understand everything, how to find P2, 3. So for this reason I will just draw rigid body number 2 and rigid body number 3. This is 2 and this is 3. And basically, what we didn't talk about it, but it can happen, that basically these two rigid bodies has a linear or transversal motion relative to each other. There is no relative rotation between them. It means that the relative instantaneous velocity should be somewhere in the infinity. So P2, 3 is somewhere this direction in the infinity, because if you have an infinite large radius circle, then the points will just traveling on a straight line. Okay, so this is the idea. So it should be somewhere in the infinity. P2, 3 is somewhere in the infinity. But additionally, we also know that the Kennedy line should go through, Kennedy line 1, 2, 3 should go through P1, 2, which is already found. So this infinite line should be placed here, because then it will go through P1, 2 as well. And it will also be in this direction, and it will go to the infinity. So therefore it could be drawn here, and here we add this notation. So additionally, this line must go through the point P1, 2 because of this circle. Okay. So finally we found out that the Kennedy line is in this direction, because P2, 3 is somewhere in the infinity down there in this direction, perpendicular to this rod. And we also know that it should be on a line which goes through this point, and putting together this information we will find out that the Kennedy line goes here, because if this point P2, 3 is in the infinity, it doesn't matter if this line is here or here, because at the infinity these two parallel lines will just intersect each other. So that's how it's go. So this is finally Kennedy line 1, 2, 3, and basically point, we can use this double notation. So this point P2, 3 is somewhere there in the infinity. Okay, we are talking about P2, 3 here as well. And it's in the infinity. And finally we found this Kennedy line. So what we wanted to do is to first find this P2, 3, and we have found the Kennedy line. So as the intersection point we basically found P1, 3, 2. So this is finally here. P1, 3 is located here at the intersection point of the blue and the green Kennedy lines. Okay, so this is how to use this circle And of course we use a lot of other things, but finally we could find this instantaneous center of velocity, and then we perform this calculation what was there. So now we are able to calculate the ratio of the angle of angular velocities. So again, we can calculate these distances. So this is the distance from point A to P13, and this is the other distance here, which is from point D to P13. And we already know this distance because this is a geometric parameter. So this is L4 here, from here to here. And there is just one arrow here because the direction of this line is important, because the sign of the omega velocities will opposite to each other, and it's because that these two directions are also opposite to each other. So finally our formula will be that omega 1 times and there is a lot of calculation here as well, so basically we should calculate this distance here, but this is equal to the length of this distance from B to C over cosine the angle of this second bar, so theta 2 is here and L2 is here. Okay, so we could compute this, and basically we say that omega 1 times this small distance here, which is L4 minus this one, L2 over cosine theta 2, is equal to omega 3 times L2 over cosine theta 2. And from this formula we can get the ratio of omega 1 and omega 3. Okay, so we can finally compute the ratio of these two angular velocities. And here we see that we have to do some additional geometric calculations. Okay, so we should calculate this distance and also this angle, so there are some additional calculations, but basically this is how this geometric approach works. And basically we arrive to a point when this formula could be somehow generalized, and it turns out that it can be really generalized for any cases. Okay, so in general we can say that the ratio of angular velocities can be calculated by a formula, and these are relative angular velocities, but we will see how to apply it. So the ratio of two relative angular velocities is equal to the ratio of two direction lengths. So this is PIK relative pole, this is PIJ relative pole, and their distance is defined, and this is PJK relative pole, and this is PIJ relative pole again. Okay, so this is a general formula which always works, but we have to define what is the meaning of omega ij, for example. So this is the relative angular velocity of rigid body number j relative to rigid body number I. So if they are rotating together, I and j, then it will be 0. Otherwise we will get some number. And these are 3 points. Okay, so P, I, K, P, I, J and P, J, K can be found by using the Aronhold-Kennedy theorem. Okay, they can be found by using Aronhold-Kennedy theorem, and basically this is what we have done. So we can create the same drawing again. We basically done the same in the previous example, but now we generalized it. So what we have done is that we had this structure. Now we are just drawing the important things, and we said that we had point P01, we had point P03, and somewhere here we had point P13, which is the relative pole of rigid body number 1 and 3. So this was number 1, this was number 3, and this is number 0 basically. And this was the corresponding Kennedy line here. And what we have done is to calculate the ratio of omega 1 and 3, or we can also calculate the opposite one, but it doesn't matter. And it's basically equal to the relative angular velocities, but they are relative to the ground. So I can say that they are absolute. And the absolute and relative to the ground is the same. Okay, so this is absolute, and this is relative to the ground, and this is the same meaning in this example, so it was fine. And what we done is just apply this formula. So it was P03, from P03 to P13 over P01 to P13. So we computed these two distances, and we apply the formula. So this is again, this distance here is from P01 to P13, and this other distance is the distance from P03 to P13, and they have the opposite sign, so therefore it will be minus something. Okay, so this is what we have done, and basically we used this formula, we applied it, and just to make it more clear, we will apply it for a more complicated problem. Okay. So we will have another example, which will be a planetary gear drive, or in other name it is also called epicyclic gear system, or epicyclic gearing. In Hungarian it's bolygómű, right? And let's create a drawing in which we try to understand the structure of the system. So there will be a part which is a straight bar basically, and it holds or keeps the things together. So there will be 3 bearings, 1 in the middle and 2 in the sides, and then there will be another wheel in the middle. So it is attached by a revolute joint here, or a normal bearing here, and then there will be some other smaller gears out here and also in the other side. So here we have this structure so far, but it only works if we attach the last part, which is basically a large ring around the whole system. And now we don't deal with the correct notation of gears, but these are really gears, okay? And the naming is that so the numbering is important, just to have the same notation as in the notes. So this is the middle gear is called sun, and its number will be number 1, and then number 0, and the ring will be rigid body number 4. So out there is the ring, which is rigid body number 4, and this carrier will be rigid body number 1. Okay, this is the carrier. Now we can get rid of the title. So this is the carrier, because it carries the 2 planet gears, but we have 2 planet gears. In more complex cases there can be 3, 4 or 5. So this is a planet gear with number 3, and the planet gear on the right hand side will have number 2. Planet gear number 2 here. And basically all of these components can rotate, and there is a certain ratio of the angular velocities in the system. So it can be used in several ways, but usually the sun is fixed, or the ring is fixed, which is outside, okay? So for example, if the sun is fixed, then there will be an angular velocity ratio between the carrier and the ring, or if the ring is fixed, then there will be some kind of ratio between the angular velocity of the carrier and the sun. So there can be different, or also the carrier could be fixed. So there is a lot of choices. So now in our example, the sun is fixed, and we will have an input motion. So this is one thing, the sun is fixed, we will have an input motion which will be exerted in the first rigid body, which means that omega 1, which is basically equal to the relative velocity of the carrier and the sun. This is constant or given, and we also know that the output is the rotation angular speed of the ring, and this is the question, how to calculate this. And now we will apply this Aronhold-Kennedy, and we will apply everything what we have. Okay, so the goal is to find the angular speed of the ring if the sun is fixed and the input motion is delivered into the carrier. Okay, so now we can just extend our figure. So now I don't know. Okay, we don't have to extend the figure, because then we will think that it's general, but it is not general. So not always the sun is fixed, it is just the case. Okay, and what we can do is to compute the output speed, and basically first we will apply this formula, the angular velocity ratio formula. We will apply for the first, which is given, rigid body, and the second rigid body, which is a planet gear. Or we could do the same, so we can also calculate the omega 1 over omega 3. So first we will be able to calculate the ratio of the input angular speed omega 1 and the angular speed of the planet gears. So we can calculate both, and these are absolute values, but we will be able to apply our formula if it is a relative angular velocity. So we should extend our notation, and we should show that this is relative to the sun. Okay, and this is also relative to the sun. So this 0 means that this is a relative angular velocity. And then by using the formula we will see that omega 1 over omega 2 will be equal to P02 P12 distance over P01 P12 distance. Okay, this is what our formula says. And in the case of the left hand side planet gear, the formula is always almost the same. We have to change 2 to 3, so P03 to P13 over P01 to P13. Okay, so these are the formulae what we have, but we don't yet have these points. Now I must get rid of this. So we should find these points, and therefore we should create some kind of drawing. So this is again the whole mechanism. Okay, this is 1 degree of freedom. We could do the same analysis to check if it is really 1 degree of freedom, but basically it doesn't really matter. So it is 1 degree of freedom after we are fixing the ground. Okay, it is 1 degree of freedom with fixed sun for example. If I fix one part, then it will be 1 degree of freedom, and we can create this drawing. So this will be rigid body number 0, 1, 2, 3 and 4, and what we need are these points, and let's check if we can find them or not. For example, P01, which is here, and now we don't write the number of points here anymore, we just draw the lines, and we know that this is P01 because it connects 0 and 1. So P0 and 1 is basically here. I think I should use some colors. Okay, so this will be P01, which is basically identical with P1. Okay, so it is given. That's fine. We should try to find P1 and 2. P1 and 2 is also easy. P12 is P12 must be here because this is the point where they are fixed together. So this is P12 and this is P13. Okay, this is P13. We can say that P12 is already known and P13 is already known. So we are just completing our abstract graph to see if we need Aronhold-Kennedy theorem or not. So these were trivial to find, and the question is how to find P02, and P02 is also easy to find because point P02, for example, is the point where the Sun and the second planet gear has the same velocity, and trivially this is the point where they are touching each other. So this point will be P02, and similarly this point will be P03 because they are touching each other here, therefore their velocity must be equal to each other, and therefore this is the relative pole of rigid body number 0 and 2 and rigid body number 0 and 3. So these are also found. So 02 and 03 is found, and we could draw a lot of Kennedy lines, but if it's not necessary we don't do it, and it is not necessary so far because we have all of these points and we are able to calculate the formula. Okay, so this is the rigid body number 0, which is the Sun. I have to save some space. Planet gear 3 is here. Planet gear 3. So I think we have everything what we need here, and let's try to evaluate the formula. So the distance from P02, where is that, to P12, the distance from P02 to P12 is here. I will use colors for easier notation, and this blue one, the distance from P01 to P12, P01 to P12 is this distance. Okay, I don't create some numbering here because that's so the colors are easier, and let's use some geometric parameters. The radius will be small r of the planet gears, and the radius of the Sun gear will be capital R, and by using this we can easily say that the red distance is just simply small r, and the blue distance is capital R plus the small r. So we can easily calculate this ratio. This is very, very cool. And we will do the same here. Now I will use a dashed line. So the distance 0, 3, 1, 3 is basically this. Okay, I have the same drawing but in the opposite direction. I just mirror it. So 0, 1, 1, 3 is from here to here, and again I can read it, but we are performing both calculations because now we will see what does it mean if it's an arrow. So this distance is minus r, and this distance is minus r minus small r. Okay, but finally they are the same, but we arrived there in different paths. Okay, sorry, this is plus. So as we said, that the angular speed of the planet gears are equal to each other, which is fine. And now we will be able, because they are touching each other, so now we will be able to calculate the angular speed of the ring. So after having these two, we will be able, so now we can say that omega 2 is equal to omega 3, which is equal to, yeah, it is equal to r plus r over r times omega 1. Okay, so this is the formula for the speed of the planet gears. And now I can get rid of this drawing, I think, for these calculations. So now we move on with the application of our formula. So now we can try, for example, to calculate this ratio. Now we directly want to calculate the ratio of the planet gear speed and the ring speed. But as we said, this is equal to the relative angular speed relative to the ground, and it means that the formula should be P04 P24 over P02 to P24. So this is our formula, and let's check if we have everything. So okay, I will draw it with blue, and then, oh no, that would be too complicated. I'm just drawing them with blue in this figure. So 0,4, let's check if we have 0,4. 0 is the sun, 4 is the ring. We are very, very lucky because they are rotating about the same point, which is here. It means that it's also identical with P04, which is identical basically with P4, which is the absolute center of velocity of rigid body number 4. So this is already done. P04 is known now. Let's check if we know P24, and we said that yes, we can calculate the location of this point because they are touching each other. So the planet gear and the ring touches each other at this point. Here the velocity is equal of the two rigid bodies. So we already done P24, and what else do we need? We also need the P02, which is already found. So that's fine. I think we have everything, right? So basically we can draw these distances. So this will be the continuous green line, P04 to 24, 04 to 24, 04 to 24 is out there here. So this is the continuous line distance. Okay, and then we need the same distance, but it measured from 0 to, so the other distance, which I will draw with a dashed line. Okay, this is dashed line. It starts from here and it will arrive to the same point. And by using this, we can create a formula. So this is this whole distance is capital R plus 2 small r over, and this is just simply 2r. So we have the formula, and then again it means that omega 4 can be calculated by just multiplying with everything and performing all of the calculations, and omega 2 is already done. So finally I can substitute this whole formula to here. So this is 2r over r plus 2r times omega 2, which is this formula, r plus r over r times omega 1. And finally, okay, it was just substituted from here. So finally, the thing is that we didn't have to use the Aronhold-Kennedy theorem because all of these relative poles were trivial. All the applied relative instantaneous center of velocities were so-called trivial. So finally we didn't use the Aronhold-Kennedy theorem, but we used this algorithmic way to compute these or just manage these points, and we also use this formula for the ratio of angular velocities, and this is only related with the distances. And the important message is that the distance is directed, so it does matter if it shows in the right or the left direction, so we always have to keep it in mind. And some additional drawing could be just to understand the problem completely and the whole idea. So as we have some knowledge in mechanics, we can draw some extra figures to understand everything. So this is the carrier, and this is the sun here, and this is the planet gear on the right hand side, and for example, this is the way how to compute, by another graphical thinking, how to compute the angular velocity of the ring relative to the sun. Okay, so this is the ring, this is the sun, and this was rigid body number 1, and this is rigid body number 2. So as we said, the velocity changes linearly, so the input velocity was given and it was omega 1. So if omega 1 is given, which is the angular velocity of the carrier, then I can simply compute the velocity of each point of this carrier, right? Here it will be negative, it doesn't matter for us. And the important thing is that I will be able to calculate the velocity of this point here, and the slope is basically omega 1, 0, okay? And another thing is that if there is another so if there is the velocity comparing to there is the angular velocity comparing to the sun, of the planet gear. So sorry, this is rigid body number 4. So I already know that the planet gear velocity in the center is identical with this velocity, which is the velocity of the carrier. But if it has some additional angular speed, then I will be able to construct this line, and I will be able to say what is the angular speed, because I know that the velocity of the planet gear here must be 0, and therefore this linear curve or linear line should be something like this. So I'm again also able to compute the velocity of each point of the planet gear, because I know the velocity here and here, so therefore I'm able to construct this line, and this line is corresponding to the slope, which is equal to the angular speed, and therefore I am able to compute the speed in the outer point here. And by using this, I'm just simply creating this construction line here, and therefore the slope of this construction line will give us the angular velocity of the ring. So this slope gives us the angular velocity of the ring, because the ring has the same speed out here, and this speed must be equal to the speed of the planet gear out here. Okay, so in this point, which is basically the relative pole of the planet gear and the ring, at this point they have the same speed, and this is also a relative pole of the sun and the ring. So here also we know the speed of the ring, which is 0, and by connecting the two lines I will be able to calculate each point velocity along the radius, and I will be able also to calculate the slope, which is responsible for the angular speed. So this idea of the ratio of angular speeds and distances is coming from here. Okay, so I just wanted to show that it is not magic, it can be simply found out how it works. So we can think it over by using this graphical idea. And the last thing for today is to apply the same knowledge for computing the ratio of input and output force and torque. And this is the last thing, and then we will talk a bit about the ending of the semester. So the last theoretical thing what we address is the ratio of input and output force or torque. And basically I think you have some previous information from some other subjects called design of machinery or something by GT3 department. So what we have is the ratio of angular speeds. We also know it, we already know it. Okay, so this omega jk over omega ik equals to pik pij distance over pjk pij distance. Okay, so this is what we have. We already know it. And the idea to obtain the ratio of the input and output torque is to say that the system is conservative. So we assume we assume that the system is so-called conservative, which means that the kinetic energy and the potential function is a constant. So there is no dissipation. That's another definition. There is a big argument about conservative systems actually, but for now we will say that system is conservative if this is true or there is no dissipation. So basically we can use the formula that the P power of the input is equal to the power related to the output. So this is the most important thing. The input power is equal to the output power, so we say that there is no dissipation in the system. And I think in some other applications you say that the input power is equal to the output power, but there is some eta somewhere, which is the coefficient of efficiency basically. So the output power is, this is the general form. So eta times the input power equals to the output power, but for now we say that this eta efficiency ratio is 1. Okay, so we don't care about the dissipation for now because it can be generalized easily. And basically what we say is that if the P input and P output is equal to each other, then the input torque times the input angular velocity is equal to the output torque times the output angular velocity. And this is so easy. And then we can also say that if there is not torque but there is force, then we can say that the input force and scalar product input angular velocity, which means that the input force is sorry, it is not sorry, it's totally meaningless. Yeah, so the input force times the velocity of the point where the input force is exerted, and this velocity will depend on the angular velocity input. So this will be equal to the output force times the velocity of the output force exertion point. Okay, so it's quite easy, and by these formulas we can simply create the ratio. So the output over the input torque is equal to what? Yeah, equal to omega in over omega out, and then you can apply this formula. So this is how it works. So if you know the ratio of the angular speed, you can easily compute the input and output torque ratio, and this goes similarly to the forces. So the output force absolute value over the input force absolute value is equal to the velocity of the point where the input force is exerted, but this is in absolute values, and this is the velocity of the point where the output force is exerted, and this is absolute value again. And here we also have the cosine alpha input and cosine alpha output. So we have these two formulae, and now we will have a very simple example where we show how we can apply these calculations. And then everything will be clear about this. So for example, which is very simple, we can apply this 4-bar mechanism. We can check this example of the 4-bar mechanism. And as we said before, the relative poles can be found easily. So you can create the Kennedy lines. We don't repeat everything. So after having the Kennedy lines, you will have the information of each instantaneous center of velocity. So this is number 1, 2 and 3, and this is P01, P12 and P23 and P03. So you have all of the relative instantaneous center of velocities. And let's say that the input torque is just simply a torque. Okay, so I say that there is an input which is m1, and additionally we have an input angular velocity, and of course the output torque will be an opposite direction after we calculate it. So this is m3, and the output velocity will be something like this. Okay, so we are just trying to, so there is a torque applied. This is a driving torque, and therefore the whole thing moves like this. And there is a loading torque which tries to brake us, tries to prevent our motion, so that's why it's opposite direction, and of course it comes from the equations too. So finally we can say that the omega 3 over omega 1, which is basically omega 30, this is a relative velocity relative to the ground, so it is actually equal to the absolute angular velocity, is equal to the P01, P13, as we said before, over P03 from P03 to P13 distance, and this is also equal to M1 over M3. Okay, that's a very important thing. And yeah, so this can be an output and this can be an input. Okay, so this is very simple for torques. And let's see how it works, how this force version works. So if forces are applied on the system, it's a little bit more complicated, but we just have to handle the scalar product. Okay, this was the output. Okay, let's draw another very quick example. So we can consider the same mechanism. I have to create a little bit larger figure because the location of the force will be important. So let's say that this is an input force here, and this is always perpendicular to the bar, and the distance from the bearing is r input. Okay, this is the distance, and let's say that the output force is always horizontal. Just to have some fun, we say that this is always horizontal. Okay, this is horizontal. and the distance is r out, and we can also draw the velocities. So here the velocity is also perpendicular to the, this is Vf in, the velocity of the input force, the point where the input force acts, and this is also perpendicular to the bar, and here the output velocity is perpendicular to the bar, but now it is not in straight line, it's not collinear with the output force, so the cosine alpha will be not zero here, but here we see that the alpha input is always 90 degrees, right? Or sorry, it's just no, it is 180 degrees, because it is the angle between the force and the velocity, and the output angle is not 180 degrees, it's just some angle what we can calculate somehow. So this is the alpha output, which is not equal to 180 degrees. It's actually time dependent, right? Time dependent angle, it's always changing as the system is moving. And finally, we can simply apply a very similar formula. So the output and the input force ratio is equal to something. So first we should say that this is so we want to calculate this, and we should say that the power is equal to each other. So the input power is equal to the output power. This is what we have, and the input power is F input times I don't use the vector notation, I'm just using the magnitude. So it is input times this distance times omega 1, and the output power is F output times the velocity here, and the velocity is R output times omega 3. Okay, this is, we should also show it. This is omega 3 and this is omega 1. And here we also have this cosine alpha out. Okay, so this is what we have. And after this, we are able to say that F out over F in is equal to R in times omega 1 over R out, which is a geometric parameter, times omega 3, which is unknown, times cosine alpha out, which is always changing. And these two things can be basically calculated with the same formula. What we have here is just opposite. I don't know why. Yeah, because we are calculating the opposite thing. So this can be just simply calculated by P03, P13 distance over P01, P13 distance. And after having it, you can just simply obtain the result for the ratio of the input and output force. And the important thing is that it is always changing, but you can do this calculation in each case. Okay, so this was the material for today, and some words about the end of the semester. So basically our communication will be done through the Moodle system, but next week there will be a Moodle test which means that not test like A, B, C, D, but there will be a sheet of questions, and the calculations must be done on paper, and the results have to be typed in the Moodle, and the Moodle checks the results automatically, but parallelly you will have to upload your handwritten document. There will be a time slot for that, so not immediately, there will be 1 or 2 hours to upload this scanned document, but there will be a very strict time range for the input of the numerical data in the Moodle system. So you have to be sure that you fill up every field with the numerical values which are the question, and then later in 1 or 2 hours you can upload your handwritten document and it will be corrected, and I'm not sure which day will it be, but I'm almost sure that it will be on Wednesday at the same time, but in the Moodle we will give you information about that. And also the homeworks will be corrected, and finally you will get some kind of mark. But in more detail we will give information through the Moodle system. Okay, so always check the Moodle if there is new information about the finishing of the semester. So thank you very much for today. I hope everything was understandable. You can scroll back in the video and look it again, and you can ask me questions. So thank you for the emails about the homeworks. I try to answer everyone. So if you stuck with the homework, you can also ask in email. So thank you very much for today, and see you. I don't say next week because now we finished this. So next week on Wednesday there will be no class because I'm almost sure that there is the time for the test. Okay, so goodbye, and good luck for the end of the semester for everyone. And one more additional information. So in the Moodle there will be a test exam in which you can just try how to handle the Moodle system, how to upload your numerical values into the boxes, how to fill the boxes. So you can just get familiar with the Moodle system itself. So it will be some very trivial mechanical problem, I think, or just you have to do some multiplication or something. You will be able to check how the Moodle system works. Okay, so that's very important to try this before the real exam or real test. Thank you very much for today.